Hi everyone, we're back here with another video on compositions and inverses. Before we talk about this, though, we have to talk about the equality of functions because this has a kind of an important role, and this has something you should see, and because it has consequences not only in this course but courses down the road. So, equality of functions says if you have two functions, we say that these are they equal each other, and we just write f equals g without the brackets of the x if both of these conditions are true. So the first thing that has to be true is that the domain of f and g must agree. They have to be the exactly same set of numbers. If they differ by one number, equality cannot occur. And then two is that, well, the obvious definition of equality has to hold for each element of x, is that, you plug in any value of x, or value in for x and f, you should get the same value out of g. So let's look at a non-example, so an example that violates this definition, so we can get a sense of what it means to be equal from it. So I have two examples: a fraction, f of x equals x squared minus 1 over x plus 1, and g of x equals x minus 1. So let's simplify f of x. Well, f of x, when we factor the numerator, we get x plus 1, x minus 1 over x minus 1. And we can cancel the x minus 1s and get x plus 1. And so you might be, sorry, I made a sign error, so let's start this video over. Oh no, we'll start from here. So we get, when we factor x plus 1, x minus 1, all over x plus 1, and these x plus 1s cancel, and we get an x minus 1. So you might be tempted to say that this equals g of x, and this is wrong, because the domain of f is negative infinity to negative 1 union negative 1 to infinity, and the domain of g of x, already here, is everything. So why does this make a difference? Well, it comes down to when I canceled here. So let me get rid of the lines and let me look at this term right here. It comes down to the cancellation of these two terms. Now, when x is not equal to negative 1, x plus 1 over x plus 1 equals 1, because you get the same number over each other. But guess what? But something special happens when x equals negative 1. Then we get negative 1 plus 1 over negative 1 plus 1, and this equals 0 over 0. And this is known as an indeterminate form. And I can't spell indeterminate today. Indeterminate form. And for those of you who are going on to calculus, you will definitely be learning more about indeterminate forms. But basically what you need to know for right now is that you cannot cancel two terms when they can be indeterminate for some value of x. So, but this equality is true because we're not allowing x to be negative 1. Notice that negative 1 is excluded from the domain of f. So this equality is true because we are not considering negative 1. If we considered negative 1, then we cannot perform this cancellation because it's of this indeterminate. Because at x equals negative 1, this would be indeterminate. And that's what's going on here, is there's an implicit that cancel, you can cancel when x is not equal to -1. So this equality here has a condition on it that we don't usually talk about because the domain is understood to exclude that value, and so we don't really have to worry about any cases here. But when we try to compare f of x, this f of x, to this g of x, we have to make that distinction because their domains are different. And this even produces different graphs. So let's look at the graph of f of x, which is x squared minus 1 over x plus 1, which we can simplify to x minus 1. And this simplification does have a use. Oh, sorry. Yeah, I got it right. So we graph this like any other normal graph. So we'll have, here's -1, 1, 1, -1. So the graph of f of x is going to look like the graph of x minus 1. So we'll have an intercept at -1 here, and we'll keep going up and over 1. So our graph, let's do this on graph paper. I should have done it on graph. My drawing is not the best. So let's do this again. So we get an accurate drawing, and then I can copy over things. So again, so we're going to have a y-intercept at -1, and it's just going to keep on, in terms of the graph paper, just going through each one of the squares. But there is an exception here. Because this function is undefined at -1, we are actually going to have a hole in the graph at that point on the line. Whereas the graph, so let's do this in a different color. So the graph of g of x equals x minus 1 does not have that hole in it. And so we can just draw a line straight through it. So that's the difference. When we make that cancellation, we basically get the correct equation for graphing, but we always have to throw this hole in. And so this is going to make a big deal in a minute when we talk about inverse functions, because we have to talk about when functions are equal. So notice when I move over here, they agree everywhere except at -1. There's a disagreement. Alright, so let's zoom back in. Let's talk about our important theorem here. So this is a theorem in your book. I'm not going to say which theorem because I want to use this more in one class. But every book that talks about composition has some variation of this theorem. So let's get the implication out of the way first and the example out of the way, and let's just focus on this. So, and let's get rid of the grid lines. So this is a very important theorem. If you have two functions, f of x and g of x, and they both have to be 1-to-1. If both of these conditions are true, so if you compose them and get x in either direction, then g is f's inverse and f is g's inverse. So notice in this, in my previous video I talked about, not only functions can have inverses, but relations can as well. So notice here we're automatically assuming that everything's are functions. And furthermore, this statement says that if these two statements are true, then G's inverse is a function and F's inverse is a function. So everything here is involving functions. We don't do anything with this theorem that is not a function. And notice this has an important consequence, because so this is a quality of functions. So notice that in particular that the domain of G inverse has to equal the domain of F if this equality is true. If this equality is true, then the domain of G equals the domain of F inverse. But we also know some things about inverse functions. We know that the domain of F is going to be the range of F inverse, and the domain of F inverse is going to be the range of F. Because all we did, this equality is justified by the fact that all we're doing is switching. When we created inverse, all we do is switch the x and y coordinates. And so all you're doing is changing the range into the domain and the domain into the range. So this equality is always true for any function. And so this leads to this implication right here, is that if, so we can read this, is that if F and G both satisfy this theorem I just had up, then the domain of F must be the same as the range of G, and the range of F has to be equal to the domain of G. So if you have two functions that are inverses of each other, the domain of the one function is the range of the other, and vice versa. And that's going to be an important fact, because we're going to see an example where if you were just to consider condition 1 and 2, you might conclude that they are inverses when in fact they are not. So let's look at an example first where we do have two functions that are inverses of each other. So we need to check two things in this example. We have to check that, let me make sure I got a good pen here. I do now. So we want to check that F circle G of x equals x. So remember from our videos on composition that we're going to write F, G, and x. We put parentheses around the x, a parentheses between F and G, and we put a parentheses on the end. So then we substitute in the expression for G of x in for it. So we'll get x plus 4 all over 3. And then what we're going to do is take this expression and plug it in for x and f. So our rule for substituting expressions is we're going to write 3 times the parentheses minus 4, and inside this parentheses will go the x plus 4 over 3. And then we just do order of operations. The 3's cancel, and we get x plus 4 minus 4, and then the minus 4 and the plus 4 cancel and gives us x. So our first condition is satisfied. Our second condition is G circle F of x. And so looking back over here, f of x is 3x minus 4. So let's do our trick here first. So we'll have G, F, and x, put parentheses around the x, put a parentheses between the G and the F, and put a parentheses on the end. And then we're going to evaluate G, and we replace f of x with what it's equal to, so 3x minus 4. And then we look at G. G is x plus 4 over 3, so it's going to be parentheses plus 4 all over 3. And we're just going to put this 3x minus 4 inside the parentheses. And now let's simplify it. So order operations say I do, let's do one extra step here. The parentheses, there's nothing we can do about them, so they go away. Then order operations say we do the addition in the, the numerator first. So you get rid of the plus minus 4, and we'll get 3x over 3. And then the 3's cancel and leaves us with x. So the second condition is satisfied. And so these functions are inverses. But there is one little thing I didn't check, which, is always in the back of your head when you're doing these problems, is that we never check the fact that these are both one-to-one. But this is a graph of a line. This is a graph of a line. It's that we have a linear function, and all linear functions are one-to-one. So there was nothing to check here. So this condition was automatically fulfilled by this example. So I didn't check it because I know linear functions are one-to-one. But in general, you do have to check this every time. The easiest way to check it right now is with the horizontal line test, which was the previous video. So let's look at another example and see what might go wrong. So here is my other example. So we have f of x squared, or f of x equals x squared, and g of x equals the square root of x. And, in terms of algebraic operations, the square root and square cancel each other out. If I have x squared and take the square root of that, I get x back. So you would hope that f of x and g of x are inverses of each other. So let's check and see if that is true or not. So let's look at f circle g of x. So again, we'll write f g x, put the x's in parentheses, put a parentheses between the f and a g, and put the parentheses on the end. And so this is going to be f evaluated at the square root of x. And so we're going to get the square root of x all squared, and just like I said a moment ago, the square root and square cancel each other and gives you x. So this condition is satisfied. So we get g circle f of x, and we have g, f, and x, put parentheses around the x, parentheses between the g and the f, and a parentheses on the end. And we're going to get g evaluated at x squared, which is going to give me the square root of x squared, and they cancel and give me an x. So you would assume that f equals g inverse and g equals f inverse. This is, let me get a different pen to highlight this, wrong. Oops, sorry. This is wrong. Wait a minute, it satisfied those two conditions. Well, it didn't satisfy that one other condition I was just talking about. This function is not one-to-one. And so this theorem doesn't apply. This theorem only applies if both the functions you are considering are one-to-one. And since this function is one-to-one, that theorem does not apply, and they are actually not equal. So let's see another reason why they are not equal. Remember, so why not equal? So let's look at f of 2. That is going to be 4, and f of negative 2 is also 4. So let's just draw our domain and range for these two values, or these 2 points. So in our domain, we'll have 2 distinct points, but in our range, we'll have 4, and we have everything, all the other numbers that are in there. And we get 2 arrows that go to 4. So this is what f models right here. But f inverse, what does that model? Well, this is going to be 2 and negative 2, and over here is going to be 4. So this 4 is going to have the arrows pointing in the reverse direction. So notice that says that f inverse of 4 is both plus and minus 2. But let's look at, for example, F circle G. Or, let me see, hold on, let me make sure I get the right order. No, I want to square it, then take the square root. So I want to do G circle F. Because F is x squared, and G is the square root function. So the idea here is that if these were inverses, I should get the same value. If F and G were the same, if G was F inverse, I should get plus or minus 2 out of this. So let's see what happens when I evaluate this at 2. So I get that we have G of F, and then we just write the 2 when we're evaluating. And so what's F of 2? Well, we put the 2 in, and we'll get a 4 out of it. And then we'll take the 4, plug it in for G, and we'll get just 2. So notice that G circle F of 2 is 2. Well, when we take F inverse, we just get plus or minus 2. So notice that so if we look at F inverse circle F of 2, we get F inverse of F of 2. F of 2 is 4 just like before, but because of this argument right here, we get plus or minus 2. So notice that on this domain element, I get two different things, and in fact, this is not a function, whereas this expression is a function. So that's kind of the issue here. You just cannot check these two conditions right here, because if you just go about checking these two conditions, then you would erroneously conclude that these two things are inverses when in fact they're not. So, but the question is, you would like these two functions to be inverses of each other. So is there something we can do to fix this? And the answer is yes. And that's going to be the subject of the next video. So our next video will be restricting domains to construct an inverse, and that's what we'll need to do to fix this. See you then.